As you can see, we have moved from the innovation of geometry on the area of AI, moving into the regulatory part, the challenges part, the energy sector. Now we are going to jump directly with Tudor Coman, who is the software development engineer in Adobe, on leveraging multi-arm bandit algorithms for the dynamic decision making. So we are going to move the flow further from the innovation approach to the challenges aspects to further innovations. So Tudor, with any further ado, welcome on the stage. Big round of applause once again, please. Thank you.
Yeah, thanks. Hello, everyone. Can you give me a thumbs up if you can hear me? Thank you. So today I'm going to be talking about how we can leverage multi-armed bandit algorithms in order to optimize dynamic decision making. So probably the question most of you have is, what are multi-armed bandits exactly? And that's exactly the same question I had a year ago. So I did what any normal software engineer would do. I went to Google and I typed in multi-armed bandits. And this is the first image that popped up. And I was like, okay, what do slot machines have in common with multi-armed bandits? And we can see that multi-armed bandits are a very common reinforcement learning problem, so basically AI. In this problem, a player has to repeatedly choose between a finite set of actions, and each action provides a random reward from a specific distribution to that action. So kind of like slot machines, if you try to find the winning one, but it can have a variety of use cases, which we will later see. And the final objective is basically to maximize the total reward that you can obtain after a number of rounds. So how is this problem helpful? First of all, in healthcare, you can use it to run clinical trials. It helps you find the best treatment while minimizing side effects. For finance, you can use these algorithms to build a portfolio if you're a hedge fund or any financial institution. And our study case will be in digital marketing is for maximizing sales, clicks, views, or other metrics in an A/B test. So what is A/B testing exactly? An A/B test is when you try to take all of the visitors that access your website or app, and you split them into groups. The most simple A/B test is when you split them in only 2 groups, but you can, of course, split it in more. And basically what you're trying to achieve is trying to find which option is the best on a metric. So for sales, you want to see which version gets the most conversions or the most clicks. It can have a variety of metrics that you can use, anything that you can measure. So our setup is an A/B testing platform where traffic is normally manually allocated by the user that defines the A/B test. In this case, our clients. And what we wanted to achieve is adding multi-armed bandits and make this manual allocation totally dynamic using multi-armed bandits. And the test, which we ran in order to prove that this would be a viable solution, we used an ABC test with 3 different conversion rates for users, 6%, 2%, and 4.5%. So in this case, the bandits can be considered Bernoulli because actions only have a yes or no outcome. These are also called coin tosses in statistics. Basically, we wanted to see which version gets the most sales. So we used 4 algorithms to see this. We used Thompson sampling, we used upper confidence bound, probably approximately correct, and lil UCB. So now let's see how these algorithms work. For Thompson sampling, it's basically a beta Bernoulli bandit, and it is called that way because it uses a beta distribution. Uh, Basically, this distribution is used in statistics to model coin tosses, uh, knowing the number of heads and tails until that specific moment. And basically, what you do with this beta distribution is that you keep the statistics for each arm, in this case, the number of conversions and the number of visits. And you use these two numbers in order to sample a random number from the beta distribution. And at each iteration, you take the arm with the maximum score. So this option explores the all of the possible arms in this setup and gradually exploits the accumulated information in order to try to maximize conversions. And this is the result that we got. We ran around 4,000 iterations. You can see that we have the percentage of views that get allocated to the winning arm. The next attempt was upper confidence bound, but we didn't get such good results. In this case, you introduce the concept of uncertainty for each arm, and that's basically included in the confidence bounds. And this is considered normally a classic approach, but our findings were that it was too aggressive, and I'll show you exactly in a second. And we had very little exploration of the possible arms, but we had a lot of exploitation. So basically, it found the winning arm very fast, but then it allocated it totally to that arm. This normally would be good because you would want all of your traffic to the arm that gets the most conversion rate. But if something changes to the setup, so let's say another arm becomes better in the future, this wouldn't be a good solution. Next was probably approximately correct. In this case, we found out that it was great for choosing more than one winning option. This approach used always valid confidence bounds. This is the formula, but don't worry, I'm going to walk through it a little bit. So basically, it takes into account conversion rate, number of views. It also has a fine-tuning parameter, which you set based on the experiments that you run. And very important, it has an uncertainty factor. What is this uncertainty factor? Is that it names, or you set it, for example, at 5%. If you set it at 5%, it means that it will give you an output with 95% statistical certainty. And this is the results that we got. We thought these results are better because it took around 1,500 iterations, as you can see, to find the winning option, and then it allocated it to that. This is a great algorithm if you have, for example, 5, 6, 7 arms, and you want to choose the top 3. For example, what I can think of right now would be in a stock portfolio. And last but not least, we had lil UCB. This is the better brother of upper confidence bound. And it basically integrates into the confidence bounds the law of iterated logarithm to optimize the number of attempts to get to the winning variant. I won't get very much into specifics, but this is the formula that it uses. It also takes into account the arm conversion rate and the number of views. And there's also a delta parameter right there that is basically the certainty factor that we talked about earlier. And these are the results that we got. This was great in our setup because it started allocating most of the traffic to the winning arm very early on, but it also kept exploring the others. This was very helpful, and we consider this the best option in this setup. But of course, all of the algorithms that I presented have a specific use case. So this is an overview of the algorithms that we walked through. We start with Thompson sampling in the upper left corner, and then going from left to right, we have upper confidence bound, probably approximately correct, and lil UCB. So some conclusions from these experiments that we ran are that even though they're currently not popular, they are a great way to optimize decision making across various sectors using AI and reinforcement learning. There's a lot of initiatives and research literature on the subject. So if you want to go further, you can read about contextual bandits, about collaborative bandits. But what I personally found difficult about this is that it's very hard to find. It's not as mainstream as, I don't know, GPT or LLMs. I also included some POC code. I would have liked to demo it today, but unfortunately we don't have the time. I don't have it documented very well yet, but if you have any questions regarding it, you can always reach out to me. So I included a list of papers that you might want to read if you're curious about this topic. It was quite difficult to find these papers, but I found them a very good read if you want to further dig into this topic. Okay, so if you want to connect with me, here's my LinkedIn and GitHub. If you scan the QR code, you will get the link to my LinkedIn. We can connect. You can ask me questions about multi-armed bandits if you have something more complex that you think about, or maybe questions related to other AI topics. So thank you very much for attending this presentation. I think we have more than enough time to address some questions.
Mike is coming to you, don't worry. Please fasten your seatbelts and have patience. It'll come. Otherwise, I'll bring it myself, no worries. I think that will be fast. Who raised your hand? You raise your hand. We have more time, so I'll give you a spot as well.
Thank you for. Okay. Thank you for the presentation. I have two questions. First of all, did you compare these algorithms with something very basic, something like epsilon greedy or epsilon greedy with annealing? And the second question would be, how do you implement a more complex problem when you know that you expect the outcome from your arms to be somehow ordered? So, for example, in this ABC testing, you don't know anything about the ordering of the expected outcomes. But for example, if your arms are something like 10% discount, 20% discount, 30% discount, you know that the expected outcome is greater or smaller, whatever, for 30, and the relationship is ordinal in the sense that 10, 20, 30 are in the bigger or smaller. It depends what you want to achieve. So in this context of ordinal arms, how do you implement it, or how do you extend the algorithms?
So regarding the first question, we tried epsilon greedy as well. It was quite a basic outcome, so we didn't get any much better results than random, for example. And what we didn't like about it is that if an arm accumulates a lot of good data, for example, in a month, and then the following month is very bad for that arm, then Epsilon Greedy will tend to allocate the traffic to that arm and not change. So it doesn't really have the ability to adapt so easily. And regarding the second question for Ordinal, I'll have to think about it for the specifics, but in this example, we only tried Bernoulli bandits, so only yes or no outcome. But normally in multi-arm bandits, you can create also a continuous metric, and you can try to maximize or minimize it. So I suppose that maybe you can integrate the time or the number of iteration or the iteration number in the formula that you use. Thanks.
Thanks. It's Max Potter. I work at Bailey Gifford, which is an asset management company in Edinburgh. Thanks for the talk, Tudor. It's really interesting. I wondered I'm having a hard time mapping it onto a portfolio construction setting because it seems more adversarial to me than the marketing example you gave. And it's more of a dynamic scenario. So how do you does the algorithm handle that? And could you maybe walk me through just how you're thinking about how it maps onto portfolio construction?
Yeah, so the idea behind the multi-arm bandit is that it can adapt very easily to changes. So that is why it could be a good scenario for financial portfolios. Of course, I'm not a financial expert, so don't take my advice on that. But I think that you can use the stock data that you get or instrument data that you get in order to know how to allocate in a certain day or for a certain period of time. I didn't test it, of course, but maybe it's something worth trying. You never know what you might find out.
All right, no more questions, I suppose. Anything more you would like to add from your end?
No,
Enough
thank you.
spotlight for today. All right, big round of applause once again, please.
Thank you.